In 1996, a committee of leading astronomers, led by Alan Dressler, formally recommended that NASA develop a space telescope that could observe the heavens in infrared light, a wavelength that enables astronomers to see through dust and gas clouds, thereby expanding humanity's view of the universe. The proposed telescope would have a diameter of more than 4 meters and operate in an orbit beyond the moon. Its powerful capabilities would enable astronomers to peer even deeper into space and understand events that occurred further back in time, providing a more comprehensive understanding of the universe as we know it today. This telescope would also capture some of the clearest images in history. After the initial recommendation for the telescope in 1996, 3 teams of scientists and engineers from both public and private sectors met to assess NASA's feasibility in building the proposed telescope. All 3 teams concluded that the telescope could be built, and in 1997, NASA agreed to fund additional studies to further refine its technical and financial requirements. By 2002, the agency had selected teams to build key instruments for the telescope and established an advisory group of astronomers to guide its construction. That same year, the telescope was officially named the James Webb Space Telescope JWST, in honor of NASA's former administrator, who made significant contributions to the development of the Apollo program. Construction of the Webb telescope began in 2004, presenting engineers and astronomers with the challenge of creating new technologies and processes to meet the mission's demanding scientific requirements. Unlike Hubble, which could be repaired and upgraded by astronauts working from Earth, Webb would have to operate at an unserviceable distance while still meeting its many demands. Despite these challenges, the team successfully completed all 18 mirror segments and conducted rigorous testing to ensure they met the required specifications. By this point, the telescope's construction was progressing smoothly, and the dream of it reaching space seemed more tangible. The construction of the James Webb Space Telescope as a whole began in 2012 and continued through 2013, with various components of the telescope being constructed at locations worldwide. In 2013, construction began on Webb's sunshield layers, designed to protect the telescope from excess heat and enable it to function effectively in space. Over the next several years, Webb's various scientific instruments were subjected to rigorous tests of extreme temperatures and vibrations, and its 18 individual mirrors were carefully installed onto the telescope's backplane structure. In 2017, all components were integrated and tested at NASA's Johnson Space Center in Houston, Texas. Despite facing the effects of Hurricane Harvey, the telescope and its instruments completed a final round of environmental testing in a giant thermal vacuum chamber to ensure their proper functioning once deployed in space. Finally, on December 25, 2021, at 7:20 a.m. Eastern Standard Time, the James Webb Space Telescope was successfully launched into orbit around the Earth. The James Webb Telescope is a powerful infrared telescope designed to observe celestial objects that are too cool or faint to be observed using traditional telescopes. These include stars, nebulae, and planets in the early stages of their development. Since these celestial bodies emit most of their heat as infrared radiation, the researchers optimized the telescope to capture this type of radiation, allowing us to better understand these distant objects. Infrared radiation is unable to pass through gas and dust, making these areas opaque to the human eye. However, the JWST can see visible light, infrared radiation, and ultraviolet radiation, allowing it to image objects obscured by gas and dust, giving us a clearer picture of distant phenomena in the cosmos. Additionally, infrared radiation can be used as a tool for studying the properties of materials on Earth, such as their chemical composition and temperature. It has many important applications in astronomy, science, and technology, helping us better understand the structure and evolution of stars, galaxies, and other astronomical objects, or it can be used to detect signs of chemical pollution in our environment. To achieve these goals, the telescope is equipped with a large mirror array, advanced imaging and spectroscopy equipment, and state-of-the-art thermal control systems that allow it to operate in extreme conditions. The telescope is designed to function autonomously in the harsh environment of space, overcoming challenges without external assistance. After the telescope launched and separated from its launch vehicle, it unfolded and began its journey to its destination, executing a complex deployment sequence along the way. This process involved several critical steps, including crossing the moon's orbit and separating into different segments before fully deploying and beginning its operations as one of the most advanced instruments of its kind. Before we delve into the discoveries that the revolutionary telescope has made, let's take a look at the process it underwent to reach space. After the initial launch, Webb solar array was deployed, and on day 3 of the mission, 2 special pallets were deployed within the spacecraft. These pallets held Webb's essential sun shields, designed to keep the telescope cool and enable it to function properly in space. The shields on the James Webb Space Telescope, JWST, play a critical role in ensuring that the telescope can operate effectively throughout its mission. On day 4 of deployment, the tower holding the instrument package was lifted to its final location and assembled, a process that involved a series of complex steps but proceeded seamlessly due to the careful design of the telescope. Following that, the momentum flap was deployed, allowing the sun's solar pressure to act on the large sun shield, creating a stabilizing force for the telescope. Next was the sun shield membrane cover release, where special covers were retracted to expose the tennis court-sized sun shields. Once these covers were removed, the sun shield underwent a membrane tensioning process, where it was stretched and its 5 layers were separated, ensuring optimal performance. The deployment process did not end there. The JWST had to undergo several other major steps while in space. On day 10, the secondary mirror was deployed, along with a support structure to hold the smaller mirror in place. Then on day 13, the primary mirror wings were extended, giving the telescope its full size and shape. Once these steps were completed, the telescope was ready to begin its mission of observing distant stars and planets. #, the real purpose of the James Webb Telescope. One of the most intriguing aspects of the James Webb Telescope is that it wasn't built to perform a single task. It was designed to address a broad range of scientific questions. The telescope's infrared capabilities allow scientists, like Daniel Einstein from the Harvard-Smithsonian Center for Astrophysics, to look back in time and observe galaxies as they were during the early stages of their formation. Because light takes time to travel, the farther away a galaxy is, the older it appears to us. By observing these distant galaxies, the telescope can examine the early evolution of galaxies and help scientists piece together a comprehensive picture of their formation and growth over time. Due to the expansion of the universe, light from distant galaxies is stretched out over time, shifting its wavelength from visible or ultraviolet light to infrared. With its large, cold design, the James Webb Telescope excels at detecting these infrared signals, allowing it to see much deeper into space than other telescopes. This unique ability enables scientists to capture snapshots of galaxies as they grow and develop, providing valuable insights into the formation and evolution of galaxies throughout the universe. #, understanding stellar formation. The JWST also has the capability to study stars from the point of their birth. Stars form within dense clouds of gas and dust known as stellar nurseries, which are so dense that visible light cannot penetrate them, making it difficult for scientists to observe these regions using conventional telescopes. However, infrared light can pass through these dusty clouds more easily than visible light, giving scientists a unique view into the heart of these stellar nurseries. Marcia Rixa, an infrared astronomer at the University of Arizona, explains that this is because red light can pass through the dust in our atmosphere better than shorter wavelengths like blue light. This phenomenon is similar to the effect observed when the setting sun appears redder than it does during the daytime. While the Hubble Space Telescope has been able to study stellar formation on a superficial level, Webb's broader range of infrared wavelengths will enable scientists to peer deeper into these dusty regions and gain a more comprehensive understanding of how stars are born and develop. Hashtag insights into black holes. Black holes are some of the most mysterious phenomena in the universe, as they are invisible due to their ability to trap light. However, scientists can observe the effects that black holes have on surrounding stars and galaxies. Using telescopes such as X-ray telescopes, researchers have been able to study different aspects of black hole physics, such as the extremely hot and energetic environment near black holes caused by the violent shredding of nearby stars. With the launch of the James Webb Telescope, scientists will be able to study black holes in greater detail using its infrared instruments. By observing the cooler gases and stars that swirl around black holes, they can gain a better understanding of these mysterious objects and the complex physics that occur near them. Despite their seeming invisibility, black holes remain an active area of research, and the JWST will continue to provide valuable data to help scientists learn more about their nature. Hashtag searching for life on other planets. Another fascinating capability of the James Webb Telescope is its ability to detect chemical signatures of life in the atmosphere of exoplanets, using its infrared wavelengths. These signs may include gases like carbon dioxide and oxygen, which are released by biological processes such as photosynthesis, as well as other chemicals associated with habitability. By analyzing these chemicals, scientists can search for evidence of life on other planets and assess the potential habitability of these distant worlds. Through its advanced technology and powerful observational capabilities, the James Webb Space Telescope is set to revolutionize our understanding of the universe, from the early formation of galaxies and stars to the complex physics of black holes and the potential for life on other planets. The James Webb Space Telescope, JWST, has the remarkable ability to detect chemical signatures of key biological molecules, such as water and methane, which may indicate the presence of life on other planets. Webb's highly sensitive instruments enable scientists to study atmospheric conditions on these exoplanets in unprecedented detail. With this powerful new telescope, we are on the brink of revolutionizing our understanding of the universe and could potentially find evidence of life beyond Earth. The JWST is equipped with two instruments that allow scientists to analyze the wavelengths of infrared signals from planets outside our solar system. This data helps determine the chemical composition of an exoplanet's atmosphere, providing an opportunity to study these alien worlds in great detail. Exoplanet science is still a relatively new field, having been pioneered only in 1992 with the discovery of the first exoplanet. Since then, thousands of exoplanets have been found, many with unique characteristics not seen on Earth. Our understanding of these distant worlds has been limited due to current technology, but with the James Webb Space Telescope, scientists can now gather more detailed information about these planets. Unlike Earth-based telescopes, which face interference from our atmosphere, Webb operates in space, allowing it to observe infrared light without obstructions. This capability gives us a much clearer view of exoplanets, their properties, and their potential habitability. JWST has already demonstrated its effectiveness in gathering real exoplanet data. Early observations have shown its capability to detect light from exoplanets using several different methods. For example, Webb has successfully imaged Jupiter-like planets, such as HIP 65426, using the transit technique, which involves observing a planet as it passes in front of its host star, temporarily blocking some of its light. In addition, Webb has detected evidence of water and carbon dioxide in the atmospheres of two Jupiter-sized exoplanets, showcasing its advanced observational capabilities. These findings suggest that JWST is performing better than expected, enabling scientists to conduct more detailed and sensitive studies of exoplanets. Webb's capacity extends beyond exoplanets. By utilizing the Doppler effect, which shifts light to longer wavelengths as objects move farther away due to the expansion of the universe, JWST can detect the earliest galaxies that formed just a few 100 million years after the Big Bang. Early observations have already revealed many candidate galaxies from this period, suggesting that the telescope can help astronomers study the universe's earliest moments. Perhaps one of the most impressive achievements of the JWST so far has been capturing the clearest image yet of Neptune's rings. This feat marks the first time Neptune's rings have been seen in such detail since NASA's Voyager 2 spacecraft imaged them over 30 years ago. In addition to revealing the bright, narrow rings surrounding the ice giant planet, Webb's cameras showed that these rings are composed of millions of tiny dust-sized particles that scatter light in unique ways. The high-resolution image also provides new insights into Neptune's complex weather patterns, including long-reaching cloud bands and turbulent storms. The James Webb Telescope is not just a tool for studying distant galaxies and planets. It is also a powerful resource for understanding planetary systems closer to home. By examining the atmospheres and weather patterns of distant planets like Neptune, scientists can gain new insights into how weather works here on Earth. With its exceptional resolution and sensitivity, JWST promises to transform our knowledge of planetary systems throughout the galaxy and beyond. We are eagerly awaiting the discoveries that the James Webb Space Telescope will uncover in the coming years.